Hi students, I'm Anu Priyadarshini, Assistant Professor, ECE Department, SRM Madurai College for Engineering and Technology. Today, we are going to see about semiconductors. Semiconductors are present in almost all electronic devices and circuits. These devices are mounted inside many electronic appliances that support our everyday life. First, we will see what is a conductor, insulator, and a semiconductor and their differences. We all know what is a conductor. Before that, what is conductivity? Conductivity refers to the capacity of a substance to transmit electricity or heat. Therefore, we can conclude that a conductor has conductivity. Wait a minute. So these are some examples of a conductor. We can say that when voltage is applied across the terminal of a conductor, electric charge carriers, usually electrons or ions, move easily from atom to atom, thus leading to the flow of electric current. So we can see here, the first 2 points are interconnected. That is, since it offers least resistance, it allows electric current to pass through it. Next one is positive temperature coefficient of resistance, meaning if the temperature increases, the resistance also increases. This point we will understand in the upcoming slides. Last point is the application of a conductor. That is, it is used in the manufacturing of conducting wires and cables. Insulator. Insulator is the exact opposite of a conductor. Wood, rubber, plastic, etc. Again, the 2 points are interconnected. Since it has high electric resistance, it does not allow the electric current to pass through it. Third point, negative temperature coefficient of resistance, meaning when the temperature increases, the resistance decreases. This also we will understand in the upcoming slide. So last point is the application. It is used for providing insulation in electronic and electrical and electronic devices for preventing electric shock. That is, when we touch electrical appliances without any caution, the electricity passes from the body to the ground. An electric circuit is completed. Therefore, we use rubber slippers. Why? To prevent the circuit from completing, since it is an insulator. We all know that. We used to do that in our homes. Okay. Next one. Coming to the important point. Semiconductor. What is a semiconductor? These are some examples of semiconductor. Silicon, germanium, gallium arsenide. So the conductivity is in between conductors and insulators. Somewhere in between. That is more than the insulators but less than the conductors. Therefore, we call it as a semiconductor. So they are used in electronic circuit fabrication, solar cells, laser diodes, etc. So we will see what is semiconductor in the next slides. Before that, we need to study what is resistivity. Wait a minute, let me take a pen here. Okay. Resistivity is denoted by rho. It is given by the formula R A by L. R takes the unit ohm. A is nothing but the cross-sectional area of the sample, which is given by meter square. L is nothing but the distance between the two leads of the voltmeter. So we will give it as, sorry. Yeah. So 1 m, cancel. So what will be the unit of resistivity? It is ohm meter. So we can say that when the resistance is high, current is less. We are by using usage of the Ohm's law, we know that V is equal to IR inversely proportional. So when the resistance is high, the current is less. We can say that the resistivity of the conductor is very less when compared to the semiconductor, when compared to the insulator. Here we can see that the metals have a typical resistivities of 10 to the power minus 6. Minus 6 is very less. So it offers very less resistance. That's why it allows the electric current pass through it. Here you can see that insulators have the resistivity of 10 to the power 9 to 10 to the power 20. For mica and all, we have it like 10 to the power 12. So it is very high, 10 to the power plus 9, 10 to the power plus 20. So it offers very high resistance. So it is difficult for the current to pass through it. Semiconductors, see, you can see here, it lies somewhere in between 10 to the power minus 3, 10 to the power 7, in between. So it is like between metals and insulators. Okay, here we can see here when the temperature increases, the resistance of the conductor also increases because of the increased collision between atoms and the electrons. So it has positive temperature coefficient of resistance. Here, semiconductors and insulators, we can see as the temperature increases, the resistance decreases. We are going to understand this point with the help of the energy band gap diagram. Okay. See here, this is a energy band diagram, valence band, conduction band. So this is a gap called as band gap or forbidden energy gap. It is denoted by e to the base g. Okay. The electrons from the valence band need to shift to the conduction band to participate in the conductivity. In order to shift the electrons from valence band to conduction band, we need some external energy, and that should be equal to the amount of forbidden energy gap. So we can see here, in case of conductor, the valence band and the conduction band overlap. So even a very small potential difference can cause the free electrons from valence band to move into the conduction band, which constitute the electric current. So here always remember, in conductors, the valence band and the conduction band overlap. In insulators, we can see it has a very large band gap. So it is very difficult, or it requires more amount of energy to move electrons from valence band to the conduction band. In a semiconductor, the forbidden energy gap between the valence band and the conduction band is very small, like about 1 electron volt as compared to the insulators. Therefore, a small electric field is required to push the free electrons from valence band to the conduction band. So as the temperature is increased, more valence electrons cross over to the energy gap to reach the conduction band, and the conductivity increases. This shows that the electrical conductivity of the semiconductor increases. This means the resistance has been decreased. As temperature is increased, more amount of electrons are moved to the conduction band. So conductivity is increased, which means the resistance decreased. So this proves that it has negative temperature coefficient. We can see that since the valence band and the conduction band overlaps in case of conductors, we can say that it is 0 electron volt. Whereas for insulators, it is about 6 electron volt. For semiconductors, it is about 1 electron volt. Like for silicon, it is 1.1 electron volt. For germanium, it is 0.7 electron volt. So 1 electron volt value is nothing but 1.6 into the 10 to the power minus 90. We can say that the conductivity of a semiconductor can also be increased by adding some amount of impurity in the pure semiconductor material. This process is called doping. Okay, we'll come to that later. Okay, this is the comparison between the conductor, semiconductor and insulator. Always remember, in conductors, they overlap almost 0 electron volt. In insulator, it is a very large band gap. So it is like 6 electron volt or 5 or more. In semiconductor, it does not overlap. So conductors, these are some examples of conductors, semiconductors and insulators we have seen in the previous slide. So before moving into to study what is doping, we should study the atomic structure of silicon and germanium. This you would have studied in your school days. Just a recall here. Let me take a pen here. Okay. The atomic number of silicon is 14, which means it has 14 protons and 14 electrons. So we all know that it is filled by using the formula 2n square, K, L, M, N orbits, etc. So n is equal to 1. So 2 into 1, the first orbit contains 2 electrons. So substitute n is equal to 2. So 2 into 4, 8. The next orbit has 8 electrons. The last orbit, substitute n is equal to 3. It is 18. It can accommodate 18 electrons in the valence shell, but we have only 4 remaining. Therefore, we have only 4 valence electrons in the silicon atom structure. Whereas in germanium, the atomic number is 32. So it is filled like 2, 8, 18 and last shell it can accommodate up to 32. But we have only remaining 4 electrons. So therefore, 4 electrons in the valence shell. This is the atomic structure of germanium. But when considering this as a solid, it is not a single atom. The atoms are grouped together to form a crystalline structure. How are they forming a crystalline structure? So this is one silicon atom. Wait here. Wait a minute. See here. This is one silicon atom which has 4 valence electrons. These 4 valence electrons are shared with the nearby neighboring silicon atoms. So it forms a covalent bond. See here. Similarly, each and every silicon atom forms a covalent bond with the neighboring silicon atom. Thus, we get a crystalline structure. Germanium is also similar to silicon. Why? It also has 4 valence electrons and it also forms covalent bond with the neighboring atoms. And again, it also has a crystalline structure inside a solid. Okay. So it is just a recall. It is very important to note that both silicon and germanium has 4 valence electrons and these 4 valence electrons are shared with the neighboring atom so that it has 8 electrons to attain a stable structure forming a crystalline look. Okay, moving on to the types of semiconductor.